normally in astrophysics, or at least for me anyways, I don't get the opportunity to make some prediction about something I haven't seen before. So usually you look at things that we have seen before and try to make sense of what we've seen. So very rarely do we get to actually make a prediction then later on see the prediction for something we haven't seen before. So this is why today's speaker is so exciting. I first met Jennifer Barnes back when she was a grad student at UC Berkeley. She got her PhD there and then got an Einstein Fellowship and took it to Columbia, which is where she is now. Her main claim to fame is that she was among the handful of theorists who managed to predict what the kilonova would look like before we actually saw one. Today she's going to be talking about panning for gold with things that go bang in the night.
Okay, all right. Thanks so much, Paul. Okay, so I just want to say thank you for inviting me to give this colloquium, and thank you all so much for being here. As Paul said, I have a somewhat cryptic title for my talk today, Panning for Gold with Things That Go Bang in the Night. So I'm just going to verbally, subtitle that, like using transient astrophysics to find the origin of the heaviest elements in the universe. So over the next hour-ish or so, this is what we have on tap. I'm going to give a very brief introduction to multi-messenger astronomy, so I apologize to the people in the audience who are already experts on this. And then I'm going to zero in on one particular question that we think multi-messenger astronomy can help us address, the origin of the R process elements. I'm going to discuss some potential astrophysical sources of R process material, including neutron-star mergers and some subtypes of supernovae. And then I will conclude, as one always does, with my conclusions. Okay, so I think with the recent discovery a few summers ago of gravitational and electromagnetic radiation from the first neutron-star merger, which of course was GW170817, as well as the start just earlier this week, I guess, of LIGO's third observing run, the astronomy community is like really firmly in the multi-messenger era, and this gives us the opportunity to address a lot of really interesting but still not totally nailed down questions involving astrophysics, such as stellar binary evolution, right? The compact object mergers that are observable by ground-based gravitational wave detectors are the final stage in stellar binary life cycles. Of course, it gives us the chance to learn more about general relativity and dynamics in the strong gravity regime. Because these compact object mergers produce astrophysical jets, we can learn something about the production and the signatures of these ultrarelativistic outflows. It also gives us a chance to better understand the neutron-star equation of state and therefore learn something about the architecture of some of the most exotic astrophysical objects that we know of. And finally, we can try to understand the origin of the heavy elements, which is what the piece of this larger puzzle that I'm going to be most focused on today. Okay, so I'm speaking specifically about heavy elements that are produced by rapid neutron capture nucleosynthesis, which is called the R process for short. So the R process produces about half of the elements in the periodic table that are heavier than iron, including a lot of your faves like platinum and gold, europium if you like to do study metal poor stars, and then of course radium and plutonium, which are very exciting. But we know that we need we need the R process to account for all of the nuclei that we see in the universe, and we kind of understand how. We understand the astrophysical sites, right, where all of the other elements are formed. We understand how these R process elements are formed, but there's still this open question of exactly where they're formed. And that's because the R process requires some really strange conditions in order to successfully occur. So in particular, the R process takes place in the presence of a very high free neutron flux, right? This cartoon gives a very, basic picture of how it works. You have some lighter seed nuclei and you bombard it with free neutrons. And the seed nuclei absorb these neutrons, and they're actually absorbing many neutrons in quick succession, and the absorption happens so fast that these nuclei, which are becoming increasingly heavy and unstable as they absorb more and more neutrons, don't really have a chance to beta decay until after the free neutron flux has dried up. So in that way, you build up these increasingly heavy and unstable elements. Okay, so that was a description in words, but let's take a look at the R process in action. So this is a really lovely video or a movie of an R-process nuclear network calculation that was carried out by Jonas Lipner using his R-process nuclear reaction network code Skynet. So there's a lot of information on this plot in the upper left here. We're just showing the evolution of the gas. So we have temperature, density, and then also the heating rate from the R-process. In this lower corner here is the abundance pattern by mass number. And then this, of course, is just the chart of the nuclides. So, more neutrons moves us to the right, more protons moves us up. And you can see at t equals 0 for this particular R-process event, we start out with some moderately light seed nuclei, and it's a little bit hard to see because these boxes are quite small. But down here in the lower corner, we have a lot of free neutrons. Okay, so let's look at what happens when the R-process starts. Free neutrons are captured, and that moves this abundance pattern over and up, and we produce some of the very, very heavy nuclei. And then, all of a sudden you can see that your evolution undergoes a kind of a turning point once the free neutron flux dries up. And now you see the composition decaying towards stability. So the stable nuclei are indicated here in these boxes that are outlined in black. So it can take a long time because some of the isotopes that are produced have very, very long half-lives. But eventually, you're going to see the composition settle into the valley of stability. It's going to produce this characteristic R-process abundance pattern, and it's going to fill out those heavy elements that we saw in the periodic table. So the astrophysical site where this occurs, as I mentioned, has been a mystery for a really long time. And the reason for that is that it's just hard to produce the necessary astrophysical conditions. So, where are you going to get a very high free neutron flux? Question? Yeah.
Question. So, in a neutron star, the neutrons are stable. They don't.
Right.
On the other hand, if you make very small nuclei, they become unstable. So, where is the transition? If you have a chunk of neutron matter that is a planet mass, is it stable or not?
Let's see. A planet mass, I don't know about.
Because in those neutron star mergers, we
Right.
don't know how big is the chunk that is being flung out.
Okay.
So
that's
how
a
big
good,
is the chunk that would be stable?
That's a good question. I've never thought of, the disruption of the neutron stars as like a chunky process. We always kind of think of it as a fluid. So, the general argument you make is that you take this neutron-rich matter, you move it out of this high-density environment. At that point, it's no longer energetically favorable for it to be like this extremely dense bundle of neutrons, and so it exothermically becomes decompressed, and then that energy provides enough heat to create nuclear statistical equilibrium, and then it moves through quasi-statistical equilibrium, which is where the seed nuclei are produced. And then the R process starts in earnest once the temperature has cooled a little more. But yeah, if we think of it.
When do neutrons start decaying? That's the question.
Oh, no, I don't think
No,
that's.
it was not that.
Okay.
There is a certain amount of mass
Right.
above which they are stable.
Yeah.
They don't care about the beta decay anymore. And it's a nuclear physics question because there are surface terms with it, and there are volume terms in the nuclear.
Wait, I'm sorry, what do you mean when you say they don't decay, or they don't care about the
Well,
rate
a
of decay
neutron
anymore?
star is a stable configuration.
Yes.
So,
Oh, sure,
so
right.
there should be some critical mass above which
Yes.
neutron matter is stable. And the question is, what
Yes.
is that critical mass?
What-
Now, obviously, when a star collapses, you make a
Right.
solar mass core that ends, iron core that ends up in a neutron star. But the question is, if you have two neutron stars
Right.
colliding, you can throw out a chunk of mass that is in between.
Yes, so I think usually the ejected masses that people talk about, both
10 to the minus 2,
10 to the minus 2 would be
3.
on the high end, so 10
Okay,
to
but
the, 10
is
to the
that
minus
stable?
3 and even 10 to the minus 4.
If it's coming out in
Yeah.
one chunk, is it stable?
I don't know, does anybody else know? I guess I,
Smallest neutron star?
yeah, or what's the smallest neutron star you could make that would still be, I guess I suspect, just based on what you see in the literature, that people find these tiny ejecta masses, and there has never been a concern that you're just going to make a little neutron star instead of undergoing the R process. But I can't. That's a kind of an indirect approach to your question. That's not something I've thought about directly. So that's very interesting.
I mean, it's less than the Schwarzschild mass. What's stopping it from turning back to the
Mm.
I was
So why
getting
dwarf?
the impression that the TOV solutions have these these two branches, right? You have the unstable branch in between, but it starts ramping back up into the neutron star branch around the solar mass, and that
I
must
see.
be.
So you're saying there is no stable solution?
I thought that was the case. Basically, that there isn't a stable neutron-rich solution below whatever that turnaround point is when they don't quantitate it.
Interesting.
Okay, yeah, something for me to look into more. So thank you, Morgan. Okay, so neutron planets aside, right, exactly where something like this could happen has been kind of mysterious because it is hard to get a lot of, just a free neutron is unstable. So the conditions under which you have this high free neutron flux is, it's been somewhat of a mystery. So historically, there have been kind of two major contenders. The original idea, back when the R process was first discovered, was that it might happen in the neutrino-driven winds that are launched from the surface of a newly born neutron star created in a core collapse supernova. A little bit later, people started thinking maybe it's not garden variety core collapse supernovae that produce the R process. Maybe instead it's a rare subclass of supernovae. So the focus there had typically been on what are called magnetohydrodynamic supernova, or MHD supernovae. So neutron stars emerged as candidate sites of the R process slightly later than core collapse supernovae. They were interesting because when you rip apart a neutron star, it's pretty easy to create the high free neutron flux that you need for the R process. But either way, when you make an argument for different potential sites, you kind of expect different patterns of enrichment. So
do the sites end up working out so that the neutron star emergers, even though they have higher yields by a factor of 100, end up being less frequent by a factor of 100 due to volume, and it's evens out?
yeah, so if you just make an argument about the total R process